What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
Welcome to another episode of the Concrete Logic Podcast, and today I have two Johns with me. So I have John Guynn with Roman Cement and John Kline with Kline Consulting. Some of you that have been following the podcast for some time, you'll remember John Kline. He came on and talked about carbon capture eons ago. I think it was 50 or 51 was the episode number. So if you go on the website, you can search up John Kline, but he is my go-to when I want to know anything and everything about what's going on with carbon capture. He gives talks all over the world. And you said are you going to Vienna, John?
Going to Vienna in May. Yep.
Yeah. So he's going to be in Vienna. So if you're listening, and by the time this comes out, this will be before John does his talk in Vienna. Please look him up. And John Guynn is with us today. He's from Roman Cement. He's also a patent lawyer, and he has a chemistry background. And I noticed you went to school at UVA. I'm in Richmond, so I'm very familiar with UVA. So I think my Hokie listeners probably wouldn't appreciate that you're on the podcast, but that's okay. We can't make everybody happy. But today what we wanted to do is both Johns, actually listen to our episode on ACI 323. We had Dr. Belkowitz and Rich Sazy on the podcast, and those two folks had very strong opinions on ACI 323. And we're all in the industry. We're all, we're going through this transition with the Type 1L cement and blended cements, and we're all learning as we go. And what we are wanting to do today is the Johns are going to help me understand how we can reduce cement content without sacrificing concrete performance. John G has done some work with Roman Cement utilizing this, and we want to, I guess, John, you're going to help me understand ACI 211.7 better. I shared with you, I've read it a few times, and it's my understanding. I guess we should start there. Is my, simple man view of ACI 211.7 is it's sharing how to proportion concrete mixes utilizing mineral fillers. And mineral fillers includes limestone. Is that a correct, simple summary of it?
Yeah, limestone is the main one that they talk about, and they also talk about leftovers from aggregate making, or the fracture of aggregate minerals. And so they don't specify what those are, but they could be other things other than limestone is one aggregate, and you have other aggregates that are, more siliceous-based, and so it permits those. Mine tailings is an interesting thing because you might consider ore to be an aggregate, and so mine tailings might satisfy 211, but I'm not really sure. So that's something that remains to be seen. I actually did recently join the committee, ACI 211 seminar committee, and I'm going to make some recommendations, or at least have a discussion with them about how I think we can strengthen the standard to help people better implement what it seeks to implement, which is the use of mineral fines to replace cement, but it still has some practical things that need to be improved.
Okay. And if folks are reading through ACI 211, if I look at the ground calcium carbonate, is that the limestone filler? Is that correct?
Well, they call it, yeah. So I guess that's the definition of limestone. It has to have a certain minimum amount of calcium carbonate. So if it does, then it's calcium carbonate or it's limestone. It kind of goes back and forth, but it treats them kind of as if they're the same thing.
But the aggregate mineral fillers are not, because
they don't. Yeah, they may or may not be. I mean, I guess if the aggregate is a limestone aggregate, then they would be. But if it's a silicious aggregate, they could be some other mineral.
Okay, so I guess could we just start with, because you're the one that pointed ACI 211 to me. So how do we balance performance when using these fillers? I guess what's your thoughts?
Okay, well, the way that we've done it, first of all, there's been a lot of talk about using nano limestone, which is very finely ground limestone. That's not something that we use or recommend. Also, in type 1L cement, when they grind it, the limestone being softer typically than the clinker, will also end up in the very fine portion of the blended cement. So whether you're using nano limestone or limestone in type 1L cement, what we use is not that type of limestone. It has a different particle size distribution. Ours is a coarser limestone. I use the word coarse loosely. I don't really mean that it's sand. It's not that coarse, but it does occupy a size gap that exists between the largest cement particles, which are around 40 to 45 microns, and the smallest sand particles, which are about 150 microns. So there's this huge gap in size that it fits nicely in, and it provides a lot of benefits. And also, coarser limestone is a lot less expensive than nano limestone. Typically, it's around 1/4 to 1/5 the price of cement. And so it has cost benefits. I think one of the things that people say is, well, you have to use a lot more of coarse limestone to get the same effect as ultra-fine limestone. But I say we don't have to, we get to. And the reason why I think that that's a positive is because what we're really trying to do is utilize it for its volume, that it produces a lot of volume, and it also creates a particle packing effect in the cement paste itself, and to some extent with the aggregate fraction. So it acts as a microaggregate, a term that John Kline likes to use. I agree with that term. It kind of bridges the size and the gaps between cement and sand. And so it's this sort of in-between material. But we have to use more of it, which means we get to use more of it. And because of it, it creates, basically acts as if it's in the cement paste. And so it adds a lot of volume to the cement paste, even though it's not cement per se, but it allows you to maintain performance both in terms of workability, and if you proportion it right with the right amount of cement and pozzolanic material and limestone and water, then you get really good strength and workability results. So we've tested this for about a decade, and we've done some commercial projects, and it's worked out very well. Implementation.
Yeah. No, that was great. I should have said the title of this ACI 211 seminar is Guide for Proportioning Concrete Mixtures with Ground Calcium Carbonate and Other Mineral Fillers. And it seemed like you were hitting on the size of the ground up limestone. So it was saying it can't be too big, it can't be too small, it's got to be a certain size. And I don't know if I could pull out, for me, there was a bunch of examples of proportioning calculations and things, and that kind of lost me through there.
Yeah.
But is there a size that you found that it points to that gives us a range, or is this based on individual mixes? It depends on, I guess the size depends on what you're doing for your individual mix.
Well, I think that we started using limestone powder long before I even read ACI 211 7R. And so we were using limestone that was actually practically available here in Utah. We still have coal mining, and there's two companies that create what's called mine rock dust, and they grind it to about 200 mesh, which is about 75 microns average particle size. And so that actually is a great position, because an average particle size of 75 microns is right in between the cement, which probably has an average particle size of 20 microns, and sand, which has a minimum particle size of 150. So it fits nicely. I think the ACI 211 might have some size restrictions. We might be slightly outside of those, at least part of it. But, there's a range of particles. They go down certainly down as low as 10 or 5 microns. And they go up as large as, say, 100 to 110 microns. So they are, as any particles, material has a range of particles. I think that the issue that I see in 211 7R, even though it says guide for proportioning, it doesn't really say anything about what proportion of cement should be replaced with what proportion of calcium carbonate or limestone. And I think that's the blind spot in this thing. And I've given some presentations at a conference called the Anna Maria Workshop. And what I tend to say is this, and this works with various limestones of various sizes, but depending on the mix design and depending on the actual particle size distribution of the limestone, when I design this, in my mind, I think of part of it as being cement and part of it as being sort of an aggregate. And so the part that counts as cement is going to replace the cement one-to-one. The part that's sort of the aggregate is in addition to the cement. And so we never replace cement one-to-one by weight of limestone powder because you need to have a greater amount of limestone powder than the cement you replace. So if we reduce cement by, say, 100 pounds per cubic yard, we might add 150 to 180 pounds per cubic yard of limestone powder. And then we will typically adjust the water so we get the right flow and the right strength with the right amount of admixtures. And it's not like if we reduce cement by 20%, we won't reduce the water by 20%, but it'll be something like 5 or 8%. Mm-hmm. None of that is really an ACI 211, but it's something that we have come across or noticed after years of testing that this is the way that you make it work.
Yeah. John Kline, did you want to say something?
Yeah, I just wanted to back out a little bit because we're getting down into a lot of the details. Fundamentally, cement's got to flow. For it to flow, it's got to be fluid. For it to be fluid, you got to coat the surface of all the particles. The finer the particle, the more surface area it has, the higher the water demand. So it's a function of both the particle size and also the porosity of the particle. On the West Coast now, we're dealing with natural pozzolans, more porous, higher water demand. On the East Coast, we're starting to get into harvested fly ash, more surface area because of the way the ash is as weathered, I'd say. So we have to add more water. So when the industry, I'm a powder guy, so I'm more on the cement side of things. And when the industry went over to well, they had to grind the cement finer to get the same strength. And that's because, as John pointed out earlier, the limestone is softer material typically. It becomes a lot finer. The finer limestone becomes nucleation sites. So we're not looking at a 1L type application where we're looking for nucleation sites. What we're doing is all of the ready-mix guys know that if you have a very good particle packing distribution, a size distribution of your aggregate, you need less paste. We're just taking that, extending that down into a finer size range. That's why I like to say micro aggregate, because it is on the coarser side, the 75, 80, 100 micron. In that range, we can fill the gaps between the sand and the other aggregate. We don't need as much paste, still get the same strength. And because we don't have the surface area, we don't need as much water. Now, that's the simplified version. John, as he says, has been working 10 years on this and has worked out exactly how to adjust the water for this change in particle size. I won't say it's a slam dunk, but what we're doing is filling gaps with the filler material. We're not trying to replicate. In fact, we're trying to go the opposite way of the well. Let's get the limestone in without the overgrinding, without the additional need for water.
Okay. Can I give a little background of how we got to where we are, Seth?
Yeah. Are you going to hit on so what I'm hearing is the water demand has changed. Is it increased? Is that what I'm hearing? Because when people hear, hey, I'm having to add more water to these blended cements, the first thing they start thinking of is loss of strength. It's more prone to crack, these type of things. And I think are you going to address that in what you want to show us, or?
Let me just jump in. If we're looking at cementitious, because we're taking out cementitious and putting in the coarser limestone, if you're looking at cementitious, the water demand goes up. If you're looking at the total concrete, the water demand goes down.
Okay.
I want to give you some background, Seth, as to how we got to where we are. Right now, I'm working with how to implement things at the batch plant. But early on, our technology looked mostly at the particle size distribution of the various components within the cement blend, if you're looking at a blended cement. Can I talk about that for just a brief moment?
Yes.
So, cement has a distribution of particles between submicron and say up to 45 microns. And the really fine cement particles will hydrate very quickly. The very coarse particles hydrate very slowly. And typically the largest cement particles will never fully hydrate. And you can imagine that if you have cement that never fully hydrates, then you're never going to extract the full strength potential of your cement. It's if you have gasoline in your car that you can't use, like there's 20 or 30% of the gasoline that's in your tank that you can't use, then it's just sort of added weight, which isn't doing anything. And cement's an expensive component, and it has all the embodied CO2, most of the embodied CO2 in concretes. Our original goal was to try to say, what is the ideal particle sizes of various materials you would put into a blended cement if you could select that? What we decided was, early on, and this was theoretical, and we proved it out later, and there's other articles that prove this, but if you were to reduce the maximum cement size down to something like, say, 25 microns, then you'd have a much greater chance of being able to fully hydrate the cement. And then we look at the ultra fine end, and you say, well, at some point, the finer it gets, it's sort of counterproductive because, maybe cement particles that are as low as 3 or 5 microns produce all the cement, all the strength that you're going to get from submicron particles, but the submicron particles just have increased water demand. Our ideal cement early on would be a narrow particle size distribution cement, say between, 5 and 25 or 30 microns. And then if you had to identify like a pozzolan or slag or something, how would you maximize its contribution to strength? Well, you'd want it to be as fine as possible. So in the ultrafine area, you would want to have a pozzolan, whether it's fly ash, natural pozzolan, or slag, or a blend thereof, in the really ultrafine area, because that's where you get the most strength from your pozzolan. The finer it is, the more it's going to react, and you might even get more strength out of the pozzolan than the cement you replace. We know that silica fume, for instance, produces tremendously more strength than cement pound for pound because of the way it reacts, and it fills in the really micro pores and creates a very tight matrix. So we thought about that. But then you're left with a very fine cement and a very ultrafine pozzolanic material, which that's still going to have a very, very high water demand. So then we said, then you need to backfill the coarse end with something that doesn't even have to react. It could be non-reactive. It could be a very coarse fly ash. It could be a coarse limestone or other mineral filler, and you could push that up. And in fact, 45 microns that's just an artificial upper limit that's based on how they grind cement. But we thought, well, we could go up to 100 microns, 150 microns. So we envisioned a distribution of particles where you had an ultrafine area with very highly reactive pozzolans, but reactivity is very subjective because it's not reactive like in the cement. They don't dissolve immediately and create this water demand issue in the same way. So they are there, but they don't negatively impact initial flow like the ultrafine cement particles. So you get a water demand decrease by having a very ultrafine fly ash. I did dedusted fly ash, classified fly ash that was like 5 microns and smaller, and it had really low water demand and produced incredibly high strength. So that's just an example. So if you had a narrow particle size distribution cement, like I said, 3 to 30 microns, you had an ultrafine fly ash from, say, submicron to 5 microns or 10 microns, and a limestone powder from, say, 20 to 120 microns, we created tremendously strong cement and mortar with very low cement content. And that's the ideal. And we have patents that go way back that talk about that ideal, both in terms of particle size selection for maximizing performance of the various components, and also particle packing. Like John Kline said, the more particle packing you have within your cement blend, the less water needs to be available to fill the interstitial voids between the cement particles, and so that also lowers water demand. So you get all these benefits when you select cement that size. John, do you want to add anything there?
I would say it's not just less water; it's also less paste. So you need less cementitious material, less water. It's basically reversing the 1L situation. Take the limestone out of the fines, add it on the coarse side of the equation, take advantage of the particle packing versus the nucleation, and you'll get the same strength with less cement.
Yeah. And as far as nucleation goes, the coarse particles still have a surface. They're not as small as the nano limestone, but they do have a surface, and it is a place where cement crystals will grow. And so they might not nucleate the same way as very fine limestone in 1L cement, but they still, I believe, do it, because we do notice that when we have limestone, if you just replace cement with a lot of fly ash, it retards setting and you get very slow strength development. But you put in a lot of this coarse limestone and you get it sets in the same period of time, and it also develops very high early 1 or 3 day strength, sometimes even higher. So the limestone powder is doing something other than just acting as a passive filler. So I believe that it is acting as a nucleation site, and because we have a lot in there could be some, release of calcium carbonate to form calcium carboaluminates, which they think occurs to some extent with the nano limestone.
Huh. Is there, other than adjusting the water, is there anything else that you're adding into the mix to, I don't know, supplement I guess the use of water? Like, um, is there something that we don't typically put in concrete? You're putting in the concrete to make it work with the additional filler that's replacing the cement?
Now, we use the same admixtures, low, medium, higher range water reducers to get the right flow. There are products that are coming out that are specifically made for mineral fillers, because the way in which, super plasticizers work is they deflocculate the cement particles because they tend to be charged and flocculate together. So you deflocculate. But when you have limestone particles, they're affecting water demand in a different way. And there are some products out there. I don't want to list any names of manufacturers, but we have one that we've used, and it creates a tremendously flowable material, better than a super plasticizer, because it doesn't create a sticky mix. It tends to reduce the stickiness and create really good flow. And that is an admixture which is being introduced specifically for, I don't know if it's for 1L cement or for the proposed increased use of mineral fillers because of ACI 211, or maybe because of the blended SCMs under ASTM 1697, but these have only been recently introduced, and they seem to be a very powerful admixture that helps our material in particular.
And we need to keep in mind that from a cementitious basis, we're reducing cement, replacing it with the limestone filler or the mineral filler. So from a cementitious standpoint, water demand's going up. From a concrete standpoint, water demand's going down.
Correct.
We're putting in less water, we're putting in less cement, so the amount of water is not reducing as much as the amount of cement. So when you look at those two in relationship, you see it going up a little bit. But if you look at the total concrete mix, we're putting in less cement, we're putting in the filler. On the total mix, it's less water.
Yeah. And Seth, we typically do use a little bit more admixture than a mix that we are replacing, because even though the water to cement ratio typically goes up in our mixes, the overall water to powder ratio goes down. And those are both mentioned in ACI 211, are the interplay between water to cementitious binder ratio and the water to powder ratio, limestone being powder but not cement, but it still does affect the rheology and the strength, and it has to be taken into consideration. So look at balance, but because of we probably save $8 to $10 a yard in cement reduction, but then we use a little bit more admixture, so the net result is still about a $5 to $7 per cubic yard cost reduction, but we do use more admixture. And some people might think, well, if you use more admixtures, it's going to make the concrete cost more, but it still costs less because of the cement reduction. So I don't view using more admixtures as a weakness. I view the cost reduction and the environmental benefits of reducing cement as opening the door to more intelligent use of the admixtures that we already have. And so through the correct use of admixtures, we can get a mix that has really good properties of flow and strength and durability. We want to mention that as well.
Yeah. Yeah, now you're talking my language. We're reducing the cost of concrete, and that was the whole origin of concrete's use in the United States, is because it was cheap and it was easy to use. Just wanted to touch on finishers will say that the more chemical you put into the concrete, the harder it is to finish. With your work, have you had any kind of feedback from finishers?
Yes. Well, let me see if I can share a slide here.
Okay.
Do this.
That'd be good.
If I can do this again. Okay. Let's see.
I would say at $7 a yard, do you think the finisher's opinion will matter? I'm not finishers out there. I don't want to sound that way.
But I want to
depends. It depends who you ask.
Okay, so let's look at this. If you can see this, we did a project with the city of Salt Lake. It was a 100-yard pour as part of an electric bus station, electric charging station. And there are 3 slabs. Ours is in the middle, so it takes the biggest brunt of where the buses sit. And then there's the outer ones, which are just the regular mixes. The original mix, this is a Salt Lake City specified prescriptive mix. And you can see that it has 611 pounds of total cementitious cement and fly ash. That's a 6.5 bag mix. It has a design strength of 4,000 PSI. It is air entrained at 6.3% to because, we have a freeze thaw issue here in Utah because it gets very cold. And then if you look at the Roman cement redesign mix, the cement and fly ash was reduced to 495, the cement down to 391. That's a 20% reduction in cement. The fly ash was reduced by a little bit, and the water was also reduced by a bit from 32 gallons to 30.1. But that's not a 20% reduction. That's about an 8% reduction. And then we have 150 pounds per cubic yard of rock dust, which is just high calcium carbonate limestone powder. And, if you look at the admixtures, the standard mix only used an amount of low-range water reducer. We used low-range water reducer and a high-range water reducer. So you would think that would create a stickier mix. But it turns out that this is the general contractor who was overseeing this project said, and I highlighted these things in yellow, and it said, I am delighted to report that the concrete has exceeded our expectations and is performing exceptionally well. As far as you talk about finishability, the second paragraph says, after conversing with the masons present that day, they confirmed that the low-carbon concrete performed just as efficiently as any 4,000 PSI mix while still being highly workable. And then the pump operator said that there was a decrease in pressure required to move the mix. So it further highlighted its workability. That's actually kind of the exact opposite of what people are saying about low-carbon concrete under ACI 323, that if you reduce cement, you're going to reduce the cement paste, you're going to have a very poorly workable mix, a very harsh mix. But it turns out that this particular mix was less harsh, or it was about the same as the standard mix. Even though we used a high-range water reducer, it wasn't stickier. It finished well. So that's not been a problem. And I think that with these new admixtures coming out that are specifically designed for mineral fillers, I think that we can get even better workability than what we got here, because that was not available to us at the time, but it is now. So workability is not something that we have had a problem with, but we do get tremendous strength. It does say in paragraph 1 that the average strength was 5450 PSI. One of the trucks came in at about 6,400 PSI at 28 days, which was incredible. Another one came in lower, and that was kind of the anomaly. So we just took the average between the highest and the lowest, and it came up to 5,540 at 28 days, and it was over 6,000 at 56. So we got great strength, great workability, and this saved about $5 to $6 per cubic yard, reduced the amount of cement by about 100 pounds per cubic yard.
And when was this one?
This was poured in September of 2022.
Okay.
And, we really expected this to launch us here in the Utah market. We've talked to UDOT. They're very interested in using it. They have these standards, very strict. They follow a prescriptive mix, and so they're not sure what to make of the limestone powder. I point to ASTM 1797 that permits limestone in concrete. I point to ACI 211-7R. They said, but what about the water cement ratio? And is the limestone aggregate, or is it cement, or neither? And so what do we do with it? So we're still kind of working through those regulatory issues with them.
So the way we calculate water cement ratio right now puts it out of the range of the UDOT spec.
Yeah, so if I go back to this previous page here, let's see. I don't really have a quick water cement ratio calculation here. It certainly is higher. Let's say if the original mix had a water to cementitious binder ratio of 0.44, ours might be 0.50, which is quite a bit higher. So, nobody would really want to use a 0.50 mix because they would think it wouldn't have the strength. It'd be too watery. But it turns out that that's not the case with our mixes. The water cement ratio is just a number. It doesn't mean anything, really. It means something to people that like prescriptive mixes, but from a performance standpoint, it's almost becoming irrelevant. So we want to try to see if we can, satisfy the performance criteria and let them sort of loosen up the restrictions on water cement ratio. But I think there's other ways to get around that. We can meet the water cement ratio if we can get at least some of the limestone to be counted as part of the cement. And I think there are some efforts to do that, both in ACI 211-7R, which I'm on the committee, and also there's a new standard, ASTM 1697, which is going to permit a blended SCM with pozzolan and limestone, and presumably the limestone in that case would be counted towards the cement, in which case we would not be penalized as we are now for the water cement ratio requirement.
So in this example, are you more on the side of, or maybe I'm understanding this incorrectly, so just correct me if I'm wrong. Are you leaning towards the side of ACI 211-7R where that's a blend? It's a filler that's replacing cement, and then ASTM 1697 would be more of a blended SCM, which would be added at the ready mix producer silo, right?
Well, yeah. Well, I mean, the limestone that we added was added at a silo at the ready mix plant. So it was definitely added, just like the fly ash would be added at the batch plant. So the fly ash, so the cement was in one silo, the fly ash was in the second silo, and the limestone was in the third silo. And that's been one of the impediments is, installing new silos at a batch plant to utilize this third material, which we can purchase in large quantities and have it shipped to the plant. I see the proposed changes to ASTM 1697 that allow pozzolan and limestone to be blended to have a blended product, which could then just be put into the typical fly ash or natural pozzolan silo. So we wouldn't then require another silo. But to answer your question, all of these are always going to be added by the batch plant unless the cement companies start to produce cement that has this amount of coarse limestone, which I don't see them doing in the near future.
So was the cement that you used in this example, was it type 1L?
Yes, it was a type 1L. And in fact, when we met with the city engineers and even the concrete manufacturer, they expressed a lot of skepticism as to whether or not our limestone would actually work in the way we said it would. Because up until then, we had tested type 2.5 cement, and they were just transitioning from type 2.5 to 1L in 2022. And they said, well, if they could add more limestone, I'm sure the cement companies would have already done it. And I said, well, we're not using limestone in the same way, and it's not the same particle size. And we say that it behaves differently and it does something different. And you'll see the results. And the results confirmed what we said was this limestone is behaving differently. Even though it's limestone, it is behaving quite differently because of the particle packing effect, the lower water demand effect, because it has much, much, much lower surface area, and the way that it's able to volumize the cement paste as a micro aggregate. It still works. So if you think about it, by using type 1L, they already reduced the clinker content of that cement by 10%. Mm-hmm. And then when we reduced the 1L by 20%, we reduced it by another 20%. Of course, it's not, if you do the math, it's not a 30% reduction, it's a 28% reduction in clinker factor, but nevertheless, basically tripled what the 1L cement was able to accomplish. And we got the same or better performance. I'd say better performance than the standard mix.
Okay, so you're proposing just a whole different SCM, is my understanding.
Yeah, I guess you could say it's an SCM microaggregate. Here's just a photograph.
Have you tried presenting it in that way? Is that how you presented the DOT?
Yeah, we presented the DOT as something that qualifies under ASTM and ACI standards, but it doesn't qualify as an SCM per se yet. Like I said, it's defined in 211 as a mineral filler. It's not counted as an SCM or cement. So right now it's kind of in this no man's land of we're not sure what to call it, but right now it's not considered to be cement. But again, I think that performance is really where the rubber hits the road. Anyway, here's just some photographs of when they were pumping it and finishing it, and they loved it. You can see that there's a gentleman here finishing it, and you can see that there's a pre-existing slab to the west of the slab that we poured, and then there's also another slab to the east of it. You can't see it in this picture, but when you go out to the bus station, you can see ours. It's slightly different tone of gray, and there's definitely some demarcations between that are obvious to where our slab begins and theirs ends. Mm-hmm. It's gone through 3 winters of freeze thaw. There's no damage whatsoever. There's no material. There's no missing material. No spalling. No surface cracks. No damage. It's performing very well. So that's a great field test. We've got quite a few other pours out there, not quite as big as this one. We've put concrete in trucks. So from the standpoint of performance, it's proven. It's just a question of getting it implemented. That's what we're working towards right now.
No chalky dust on top?
No. Well, actually, because it's larger than the cement particles, it doesn't really create that kind of chalkiness. No, we never had that issue.
Yeah. Huh. It took me 38 minutes, but I finally figured out what you're doing.
Okay, well, that's better than some people never understand what I'm doing. I met with a concrete company a few years ago. They gave me an opportunity to redesign their mixes. They're a national concrete company. I don't want to mention who they are, but we were at their test facility, and they ran some side-by-side tests. And later on, I was talking to their quality control person or R&D person, and that person said, "I have no idea what it is you're doing." And I tried to explain it, and they never really quite understood what I was doing. And to me, it seemed really simple. It's very straightforward, but I guess if it was that simple, then people would grasp it easier. So I'm glad you got it in 38 minutes.
Thank you. John, Kline, have you got a perspective from the cement folks? Or, I mean, do they really care?
Well, we've had discussions with different cement companies, and they basically say, "Oh, we knew that," or "We understood that," but they're not using it. Now, anytime you reduce the amount of cement and concrete, you're kind of hurting their business. But this would be something John and I have talked about it. We presented on it. This is something that would be fairly easy for a cement company to do, just to modify the particle size distribution in their cement particle by adding the stuff in at the cement plant. You know, it could be dust from their crusher operation. It could be something they're producing. It's all about particle size and water demand.
Correct.
And balancing those two.
Yeah, John, we've talked about this, and I think that there might be a company in South America doing something like that. What I would propose that a cement company could do would be, in my mind, they would create a one-piece cement where they intergrind cement and pozzolan, and maybe they could grind it finer than usual, because even though it's going to be finer, they can then backfill it, like John said, without intergrinding with the raw kiln feed, which is typically a lot coarser than the cement clinker is ground. And it is around the 80 to 120 micron size, as I did some research. And so it creates an ideal situation where they can do it. They could blend it at the back end. The result would be a cement that, it has more limestone powder than the cement it's replacing. So when you use it at a batch plant, they would have to use a little more of that blended cement than they would use currently and make some adjustments to the water and the admixtures. But that's a way in which a cement company could actually implement this technology.
Yeah, I'd be more of a proponent of, let's just stop messing with the cement. Let's all get used to type 1 and let the ready mix producer deal with the new SCM and let them experiment with the SCM, because I think we keep fooling with the cement. I think we're confusing everyone. I think
some practical things, Seth, is that depending on the strength and the mix design, you're not going to always want to have the same ratio of 1L cement with this blended pozzolan or blended SCM, if you will.
Right.
But depending on the mix, you might have different amounts of, different mixes right now have different amounts of fly ash or natural pozzolan anyway, different ratios of cement and pozzolan. And we're going to want to be able to have the batch plants have maximum flexibility to be able to adjust the amounts of these materials. Now, you get maximum adjustment if you put all three components in a different silo. But like I said, a compromise might be this blended SCM with pozzolan and limestone that would at least permit us to not have to use another silo. It would then fix the ratio of pozzolan and limestone, but that's not as big of a deal as the ratio of this blended material compared to the cement. That's the ratio that we want to have maximum flexibility to change at the batch plant.
Yeah.
I would agree with John. I mean, ideally, mixing it at the batch plant gives you the most flexibility as a concrete producer. This job I can adjust this way, this job I can adjust that way. Unfortunately, beyond the powder side of things, if the cement guys can't get their CO2 down, the high cost of carbon capture could put some of these guys out of business, which isn't going to help anybody either. So there's kind of a trade-off there if they can get it down at the cement company. But from a flexibility and overall efficiency standpoint, I agree with John. It should be at the ready mix. The magic is understanding how the particle size impacts the water demand and,
Well, one
and
of the
knowing
things,
what you're going to get out of each portion. And that's what John brings to the table.
the cement companies could probably take advantage of this if they were they themselves make the blended SCM, because, for example, I know that Geofortis here in Utah, their plant here in Utah was recently purchased by CRH. And so they are now under the same umbrella as Ash Grove Cement here in Utah. And also one of the ready mix producers is also owned by them. So I can envision the natural pozzolan that's being produced in Utah being blended with a limestone powder without grinding, so you can get the right particle size ranges. And then they could sell that as a blended product. And maybe by selling the cement in tandem with this blended product, then the cement companies might get credit for having produced a low carbon cement anyway. So that's just an idea.
Yeah, or we can just reframe it somehow and get everyone to look at the concrete carbon footprint versus the cement, I guess, because we're reducing the amount. I feel like we're chasing our tail. We could just reduce the amount of cement before we did all this. But anyways,
Yep.
But yeah, this was great. This ties into a bunch of episodes that we recently had. I was just looking through these on top of the ACI 323 episode we talked about it. Folks might want to check out. We had Tyler Lay on. We talked about the rise of blended cements. That's episode 103. John, what you're talking about too, John G, you're talking about a performance spec versus a prescriptive spec. We discussed that with Colin Lobo on episode 108. Let's see, what else was I going to point folks to? So if some of these things we're talking about, you might want to review these episodes.
Yeah.
And the ACI 323 episode is episode 109. So if you're listening, you might want to review all those and then listen to this again, because I know I'm going to listen to this again. Was there we mentioned ASTM 1697, and you said it is under review for maybe revision. Is that what you were saying?
Yeah, my understanding is I was talking to somebody who said that they're talking about, in fact, I saw some of the revisions and some of the presentations. We're talking about allowing a blended SCM that contains limestone. I want to make a couple other points. First of all, that Orange Street project, we entered that into a contest or whatever with the National Ready Mix Concrete Association, National Ready Mix Concrete, NRMCA, not one of the awards. I think there were 48 contestants, and we were one of the 12 who were given the awards. It was considered to be a very good low carbon concrete thing. I want to share the screen. Maybe we don't need to share the screen, but we have durability tests now. Some people have been saying, we've been talking to some of these engineering companies, Bechtel, one of them, and they said, well, we want to see, this was last fall, we want to see durability testing. So we now have durability tests, and we perform the same or better in all categories as the standard mix that we redesigned. First of all, I can show the screen, but it's just a bunch of numbers. In terms of ASR reduction, we reduced ASR between 20 and 33% compared to the standard mix, which contained a natural pozzolan known to be very good at reducing ASR, even better than fly ash. And we further reduced ASR. Now, why that is probably because we reduced the cement by 20%. And the cement contains all the alkalis that are going to contribute to ASR. So by reducing the cement and putting in limestone, which does not contribute alkalis, that we're reducing that. Plus, I believe that because of particle packing, we have a denser cement paste. So it's going to be more difficult for ions to penetrate through. We still have air entrainment, though. So those microscopic bubbles are still there to prevent freeze thaw. And that's also borne out by some of the tests. So we have fewer average coulombs of charge going through. So it reduced salt incursion. Resistivity went way up. It's in a different category. Freeze thaw damage, we were in about the same category. Scaling, we were off the charts better than the standard mix in terms of scaling when exposed to salt. Accelerated scaling. And then as far as shrinkage goes, it showed that we had about the same shrinkage, although there are articles out there that say the use of limestone powder should, because it's a microaggregate and doesn't react and doesn't shrink while it's during the hydration process. It should act as a microaggregate in the paste to restrain shrinkage. And that concrete company that I told you about before that did some side-by-side tests, we always reduce shrinkage compared to their mixes every time. So I believe that there are durability tests that show that not only is ours perform well in the other categories, but in terms of durability, it's very good. And I did mention this when I went to the World of Concrete with one of the cement experts who was talking about admixtures to reduce ASR. And I said, we are reducing ASR more than your admixtures are by just doing this substitution of limestone with cement. And it's not to say that your admixtures wouldn't work with ours, but this is it's like an add-on that helps to reduce it a lot.
Well, I would say that I know we have to do all those durability tests, but if you can go out there and point to something that's 3 to 5 years old from when it was placed and do those tests, I think be interesting to take a core of that slab and see what the strength comes up with, because we all are so fascinated with 28 days, but we really don't study anything beyond that and what concrete does beyond that. So I think that would be interesting as well. Taking the last episode we released, we talked about petrographic analysis. If we took that and looked, it'd be interesting to see what your concrete looks like under a microscope versus what we typically use. There's pockets of cement that are activated in concrete that we use today. So if you look at yours under a microscope and there's not those pockets, that could be interesting. Yeah. So, I mean, there's a lot to do there, but if you can convince a DOT, at least, after doing this podcast for a few years and talking to people that are coming out with innovations, it seems like if you can get the DOT on board, it opens the doors to many things out there.
Well, if anybody wants to see some of the durability test results and also, I think, mention of the award we received from the National Ready Mix Concrete Association, you can go to our website, which is www.roman-cement.com. We put the hyphen in there because it's easier to spell out. And also, early on, Roman cement jammed together spells romancement. And I think we've been blocked when I send emails because people might think that I'm sending some spam about some kind of dating site. So we put in there to eliminate that problem. But www.roman-cement.com. The website is still a work in progress, but a lot of the basic information is there, and it's just going to get better.
Yeah, that's great. No, we'll stay in contact. John, Kline, do you want to share how people can get a hold of you?
I would say just join me on LinkedIn and you can see my escapades there. I would close by saying you get all the environmental benefits of a well without some of the issues, and you're saving cost.
But just one last thing. If people want to contact me directly, john.guynn, Guynn at roman-cement.com. And I'd welcome any questions, and I would answer anything that people would ask me.
Yeah, I appreciate you both coming on the show today. I'm glad we finally got to do this. And it's interesting, and I think people should look into it. It's a different way of producing concrete, and we all have this challenge on our hands to reduce our carbon footprint. So I think this is a novel approach. So thank you, John Kline, for connecting us. Thank you very much.
Thank you, Seth.
Yes, sir. And folks, until next time, let's keep it concrete.
Okay.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
Ring, ring, that alarm always sings. Couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives. Dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. getting dirty for a clean dime. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to